Okay, so can you see my presentation?
Okay, all right.
Okay, so hello everyone. My name is Paweł Jurczenko, and today I will be talking about multi-threading on the JVM platform. A quick info about myself. I work as a senior software engineer at Allegro. Allegro is the biggest Polish e-commerce platform, one of the biggest in Europe. At the moment, we have around 1,000 microservices. Most of them, like 90% of them, are JVM ones. Usually they are Java ones, then they are Kotlin ones, and then they are Scala ones. And Scala is the language I have been using for the last 5 years now. Things I'm interested in are distributed systems, concurrent computing, and functional programming. Okay, so how will this presentation look like? The presentation will have a couple of sections, and my purpose today is to show you a wide range of many different aspects when it comes to a modern multi-threaded JVM application. We will not have that much time to go into very deep details in any of these sections. However, if you'll have any questions, feel free to ask them, and I will try to answer them after the presentation. Okay, so let's start by saying, how can we think about multi-threaded applications in the first place? And the way I like to think about them is to visualize them as a layered architecture. So we have a couple of layers, and each layer is built on top of the abstractions that are provided by the layer that is directly below. On each of these layers, we have a concept of a thread, and depending on the layer, this will mean something slightly different. At the bottom of this hierarchy, we have a physical hardware layer where a thread is not a concrete abstraction, but more of an ability to perform a sequence of instructions. A layer that is built on top of the hardware physical layer is called the operating system layer. And here a thread is a concrete abstraction that we can manipulate on and we can have references to. The next layer, a layer that is built on top of the operating system layer, is a layer, an application layer, which in case of the JVM platform is a layer of JVM threads. If on the layer of JVM threads, we create another multi-threading abstraction, then we call such layer a layer of green threads. And basically nothing stops us from going even further into this hierarchy and create our own custom multi-threading abstraction on top of green threads. Of course, as long as we have a use case for that. There are also two terms related to this hierarchy. The first one describes how threads from the higher layer will be executed on threads from the layer that is directly below. And this concept is called scheduling. And we have two main types of scheduling. The first one, preemptive scheduling, is where the scheduler is in the full control of who executes when. In the cooperative scheduling, it's where the thread is in the control. It's where the thread has to explicitly yield control back to the scheduler. The second term describes what is the relation between threads on the neighboring layers. And this concept is called a threading model. And we have three main threading models. The first one, which is called one-to-one, is a model where each thread from the higher layer will have its counterpart on the layer that is directly below. And this is the model that we have between the JVM threads and operating system threads, which means that if we create 10 JVM threads, we will also have 10 underlying operating system threads. The second threading model is called M2M, which means that M threads from the higher layer will be executed on N threads from the layer that is directly below. Okay, this is the model that we usually have when it comes to green threads, not only on the JVM platform, but in like modern software development in general. In case of the JVM platform, though, this might mean that we will be executing, for example, 1 million green threads on top of 10 JVM threads. And the third threading model is called M-to-1, which means that M threads from the higher layer will be multiplexed and executed on a single thread from the layer that is directly below. And this is the model that can be usually found on platforms that don't have native support for multithreading, for example, on JavaScript. JavaScript is a single threaded runtime, and green threads allow you to have such multi-threading abstraction on top of such a single threaded runtime. Okay, so I started talking about green threads. What are they like in general? Okay, so in general, they are regular threads, but they are managed in the user space instead of the kernel space. Also, they are scheduled by the runtime library of the language we're using or the virtual machine of the language we're using. Usually, but not always, they are scheduled cooperatively. This, of course, depends on the concrete implementation, but there are some implementations where green threads are preemptive. And examples of green threads you could heard of are coroutines, which are implemented in Kotlin, are Go routines, which are implemented in Go, and fibers, which have many different implementations across many different languages. Why do we even have to care about something like green threads? Why do we need another layer of multi-threading? Okay, so it turns out that JVM threads are an expensive resource. They are expensive when it comes to creating them, coordinating them, synchronizing them, and also to context switch between them. So by introducing such another layer, we might provide a more lightweight abstraction of threading models. This means that we might lower the costs of thread management in our application. Also, because green threads are like more lightweight and more fine-grained abstractions, they will allow us to use resources in our hardware more precisely, more efficiently. Also, by having such another layer of multi-threading, we might achieve different semantics when it comes to blocking, because blocking from now on might be blocking the green thread only, and this will not necessarily propagate as a blocking of the underlying JVM thread. Also, because of that, because green threads are a very lightweight abstraction, they can be created in like thousands or even millions. They don't have to be pulled. They can be created as they are required as the application goes. Okay, and as I said, in case of platforms that don't have native support for multi-threading, green threads allow us to have such multi-threading abstraction on top of such single-threaded runtimes. Okay, so when it comes to concrete implementations of green threads, we have many of them across many different languages. We will not go into details. We will not compare them because the idea behind them is exactly the same. They differ only in implementation details. Okay. For example, outside of the JVM platform, we have Go routines in Go. We have Haskell threads in Haskell, and we also have Erlang processes in Erlang. They are called processes and not threads because they don't share memory. Okay, they communicate solely by message passing. In case of the JVM platform, we have two types of solutions. We have solutions that we already have and that we already can use on production, and solutions that we will have in some foreseeable future. In the first group, we already have an implementation of coroutines in Kotlin. We've also had for many years an implementation of fibers in Java, which was Project Quasar, and also for a couple of years now we have a couple of implementations in Scala as well. So we have fibers in Monix. We also have fibers in Cats Effect and in Zio as well. When it comes to future solutions, we will have Project Loom. Project Loom will provide native support on the JVM platform for continuations and virtual threads. But what are they? What is the difference between a continuation and a virtual thread in the first place? Okay, so in general, continuation is a sequence of instructions that might be suspended and resumed at some later point in time. Okay, a virtual thread, on the other hand, on itself is also a continuation, which might consist of other continuations as well, and all of that will be scheduled in the runtime of the JVM application by some thread pool. In the current proposal of Project Loom, this will be fork join pool. Okay, so what is Project Loom all about? Okay, so as I said, it will provide native JVM support for continuations. On top of continuations, Project Loom will create a concept of virtual threads, which are green threads, as I have shown you. Virtual threads basically will look in the code just as regular threads. They will also be implemented by the exactly same class, thread.java class. Okay. However, in the runtime, they will have different characteristics than regular JVM threads. And basically, authors of the Project Loom will adapt or transform JDK internals in a way that will understand whether the code is executed on top of a regular thread or on top of a virtual thread instead. And such internal JDK code will be able to benefit from that depending on the context, okay? In case of blocking operations, this means that, for example, a blocking JDBC call running on top of a virtual thread from Project Loom will block only the virtual thread, and this will not propagate as blocking of the underlying JVM thread. And all of that will be basically available like for free out of the box just as soon as Project Loom is released. Okay, and let's see an example of that. In this example, I'm using thread.sleep method, which all of you are probably aware of. And this method will be changed, or already is changed, by the authors of Project Loom in a way that understand whether the method was invoked from a virtual thread or from a regular JVM thread. And depending on that context information, it will behave slightly differently. Okay. When it's being executed on a virtual thread, the runtime characteristics of that sleep method will be different than the one we've known for like 20 years now, because we will be sleeping and blocking the virtual thread only, and this will not propagate as blocking of the underlying JVM thread. Of course, if the thread.sleep method is invoked from like a regular JVM thread, then we will get the semantics that we've had for 20 years now. We will be sleeping and blocking the JVM thread. And basically, like most of the JDK will be adapted to virtual threads in one way or another. So most of the JDK will behave or will benefit from virtual threads. I used the word most because it won't be 100%. There will be, unfortunately, some corner cases where blocking on top of a virtual thread will also result in blocking of the underlying JVM thread, but those will be corner cases. Okay. What else do we gain by having green threads? What else do we gain by having that another layer of multi-threading? Well, it turns out that we can re-implement or rethink the way we've been using concurrency primitives, because we got the additional semantics of blocking on a higher level without blocking something on the level that is directly below. So, for example, locks or semaphores that traditionally were blocking abstractions, when running on top of a green thread, will also be blocking, but they will block the green thread only, and this will not propagate as blocking the underlying JVM thread. So basically, all of the concurrency primitives we've known might be reused in a way that doesn't block the JVM thread. Okay, and let's see an example of that. In this example, I'm using a traditional Java concurrency primitive, which is array blocking queue. Okay, sorry. So this is a data structure that might be used for example, inter-thread communication in your application. And let's see what happens if we try to put an element into the queue when the queue is full. Okay, so we have three possibilities to do so. The first one is called add, and when the queue is full, the method will throw an exception. Okay, the second method, which is called offer, will unfortunately return a flag, false. The element wasn't added, the queue was full. And the third method will block the underlying JVM thread until there's space in the queue again. Okay, so as you can see, we have three options and none of them is like perfect. All of them have some drawbacks. Can we do something about it? Well, of course we can, but we would have to use a different implementation of a queue, an implementation that will be running on top of green threads instead directly on JVM threads. Okay, and for this purpose, I'm using Monix library and its concurrent queue data structure. It's a completely different implementation than array blocking queue, but in essence, they will behave the same. In essence, they can be used, for example, for inter-thread communication in your application. Okay, the difference is that Monix concurrent queue runs on top of fibers. And as I said, fibers are green threads as well. So let's see what semantics we'll get in the runtime here. Okay, so we create a concurrent queue and we try to put an element into the queue. What happens now if the queue is full? Well, it turns out that the fiber that the operation was running on will be suspended, and the thread that the fiber was running on will be released to the thread pool, and basically the thread might be now reused by a completely different computation. Okay, and now we will start an asynchronous and non-blocking waiting for the space in the queue. And when at some later point in time there's space in the queue again, the fiber will be awakened. Some thread from the thread pool will be assigned to the fiber, and we will continue the operation, and the operation will probably succeed. Okay, all of that, including waiting for the space in the queue, will be non-blocking. There will be no blocking of any underlying JVM threads. Okay, so I started telling you about non-blocking IO operations, and I would like to stick to the word of such operations for a while, and I would like to focus on non-blocking IO operations. So before that, we have to see what's the difference between like an asynchronous execution and a non-blocking execution. So asynchronous execution, from the point of view of some control flow, is any execution that happens outside of that control flow, on different control flows. Okay, so this is asynchronous. Non-blocking, on the other hand, means that we don't block the underlying thread for the time the operation is performed. Okay, why do we even have to care about non-blocking IO operations in the first place? What is the problem with blocking IO operations? Well, the problem is that very often, if you have blocking IO operations in your JVM application, you will also have a lot of threads in such application, and it's a problem. It's a problem to have many threads on the JVM application, and there are many reasons of that. The first one is that we will have an increased memory consumption. Okay, so by default, a single JVM thread will require 1 megabyte of memory. So if we have 1,000 threads in the JVM application, we will require 1 gigabyte of memory just for the sake of maintaining those threads. Okay, the next problem is that if we have a large number of threads, we will also have a large number of context switches. We will basically be constantly switching the context between threads, and we will pay the price for constantly switching the context. We will pay the price for the overhead. Also, if we have much more threads than we have CPU cores in our hardware, then we will decrease the throughput of our computations. Okay, throughput sensitive applications prefer or work optimally when the number of threads is very close to the number of of CPU cores in the hardware. Okay. The next problem is that if we have a lot of threads and a lot of context switches, then we will also have a lot of cache misses, because we'll be like constantly clearing and repopulating cache values. Such application might in effect behave like there's no caching at all, but in reality it might behave even worse, because we will pay the price for constantly clearing and caching the cache values. Okay, so we will pay the price for the overhead basically. The next problem is that every JVM thread is also a root of garbage collection process. So if we have a large number of JVM threads, we might increase the time it takes to garbage collection of our application. And the next problem is not necessarily related to the number of threads, but more to the blocking nature of them. If we have a lot of blocking in our application, then we unfortunately increase the risk of having a deadlock or a live lock in such application. Okay, what about non-blocking operations then? Well, there's a common misconception about non-blocking IO operations. And the misconception is that non-blocking IO operations are about better performance of the IO operations themselves, which is not the case. And there are two reasons for that. The first one comes from physics. So regardless of the API type we'll be using, blocking or non-blocking, the operation will have to be performed like in a physical sense. Okay, so if we want to send, for example, 1 GB of data over the network, all of the bits that are part of the 1 GB will have to be converted into an electrical signal and will have to be transferred over the wire. And the API type doesn't change that. Regardless whether it's like blocking or non-blocking IO operation, okay? So this is the first reason. The second reason is that at the lowest level, IO operations are asynchronous already, okay? Because they are working using CPU interrupts. So what is blocking then? Well, blocking is an abstraction provided at the level of the operating system. This means that non-blocking IO operations are not about better performance of the IO operations themselves. Instead, non-blocking IO is about more efficient, more precise usage of resources we have in the hardware. This, on the other hand, might result in a better overall performance of our application, but this will be like an indirect consequence of using non-blocking IO operations and not necessarily the direct consequence. Okay, when it comes to like support for non-blocking IO operations in your JVM application, this depends on the operating system that will be running your JVM application. For example, in case of Linux, we have a couple of system level capabilities here that allow you to have a non-blocking IO communication. For example, we have EPOL, which is mainly used for network sockets and pipes, and not necessarily for files. Now, we have asynchronous IO, which was supposed to solve the problem of file-based operations on Linux, but for many reasons, it unfortunately didn't solve those problems. Sorry. And we have a new kid on the block, which is called IO Uring, which mainly aimed at solving the problem of file-based operations on Linux. But the solution is so general and so extendable that that it might be used for network sockets, files, pipes, and all of that. Okay, so it will be like it already is like a very general, very extendable approach when it comes to supporting non-blocking IO operations on Linux platform. Okay, let's see at concrete types of external IO communication and the support for that communication on both the operating systems and the JVM itself. So when it comes to like non-blocking network communication, we usually don't have a problem. Operating systems support that well. The JVM itself supported well. We also have like many HTTP clients, non-blocking HTTP clients on the JVM platform. We have, for example, async HTTP client, which is already quite mature and quite popular in the Scala ecosystem. We also, in the world of Java, Kotlin, and Spring, have Spring Web Client, which is also a non-blocking HTTP client. And since JDK 11, we have a non-blocking HTTP client that is part of the JDK itself. Okay, so it's a part of the development platform. Okay, when it comes to file-based operations and performing them in a non-blocking manner, there are a couple of problems. The first problem is that not many operating systems support that well. Okay, and unfortunately, Linux is not one of them. At least it wasn't until IO Uring was released. Okay. By the way, IO Uring was presented around May of 2019, which is like the last year only. Okay, so it's not yet fully employed on the JVM platform. Okay, which means that currently, if you are running your JVM application on top of Linux, you don't have a non-blocking file system operations. Okay, at least until IO Uring is more popular in the JVM ecosystem. Okay. Java new IO package unfortunately doesn't change anything here because files and classes like asynchronous file channel are asynchronous as the name suggests, but they are blocking under the hood. Okay, so they are using a thread pool in their internals, okay, and regular JVM thread blocking. And all of that affect not only the JVM platform, all of that affect other platforms as well. For example, Node.js and its libuv library that is running under the hood are also affected by that. That's why libuv running on top of Linux will also use a thread pool to perform file-based operations. As I said, all of that might change with IO Uring, but the JVM platform will have to adapt to that kernel module. And for example, people behind Netty are already working on that. Okay, so this is work in progress already. Okay, the next type of external communications are non-relational databases. Okay, and when it comes to non-blocking communication with them, we usually don't have a problem. Non-relational databases are younger than relational ones, so their clients very often already provide some non-blocking and asynchronous capabilities. For example, we have async driver for Mongo, we have DataStax Java driver for Cassandra, we have Lattice for Redis, and many more clients for other databases as well. So usually not a problem in the world of non-relational databases. When it comes to relational databases, on the other hand, we have problems with communicating in such databases in a non-blocking manner. And the problem, there's one main problem here. The problem is called JDBC. Okay, there are a couple of problems with JDBC really. The first one is that it's quite an old technology already. It's more than 23 years old now. The API of JDBC is completely blocking. The API is also very low level, like it has many leak abstractions. It also has nulls, exceptions, side effects, basically all of that we functional programmers of Scala don't necessarily like. However, if we forget about JDBC for a while, a couple of options arise in this space. There are two types of solutions here. We have low-level ones that will look and feel similarly to the JDBC itself, but they will be non-blocking instead. And we also have some high-level solutions here that will provide, for example, some DSL for the database operations. And this is how Quill works, for example. It provides a DSL for your database operations, but under the hood, it allows you to have a non-blocking communication with PostgreSQL and MySQL. Okay, when it comes to generic solutions to non-blocking IO communication with relational databases, by generic, I mean the solution that will work with many different databases, not only Postgres or MySQL. We already have two approaches to that, and we will get to that in a moment. I will show you some examples of that. Now I would like to show you an example of how far can we go with being reactive and non-blocking in the application, even though we are using relational databases, okay? So I would like to show you that relational databases don't have to stop us from going fully reactive and fully non-blocking in our JVM application. So the use case we would like to solve here is as follows, okay? So let's assume that we have a relational table and each time some new row is inserted into the table, we would like to react at the application level and perform some logic related to that, okay? So in case of the specific use case, in my company, the main abstraction that we are operating on is called an offer. You can think of an offer as a product, as a bike, as a smartphone, as a book, all of that. And let's assume that we have a table, relational table with offers, and each time a new offer is inserted into the table, we would like to perform some application level logic, okay? So what options do we have now, okay? So the first, like the traditional solution to that problem would be to just periodically, every couple of seconds, every 5 or 10 seconds, ask the database the same question. Hey, have some new offers arrived in the table? And very, very often in many applications, this solution will work completely fine. And I'm also using that solution in many of my applications because this solves many problems in a convenient way, okay? However, sometimes we would like to react much faster than a couple of seconds, than each couple of seconds, okay? And such pool-based approach will not necessarily fit our needs here, okay? So instead of a pool-based approach, we would require a push-based approach instead. But is it even possible to have a push-based approach in the world of relational databases? It turns out that yes, that it is possible, and I would like to show an example of that. Okay, to achieve our goal, we need 3 different ingredients. Okay, so the first ingredient we need is a way to react to a change in a relational table. Okay, so we already have such mechanism. We've had that for many, many years. It's called triggers. Okay, so a trigger will be awakened each time a new row is inserted into the table, a new offer is inserted into the table. So this is the first ingredient. The second ingredient is a way to push the data from the database to somewhere else without necessarily caring who will be receiving the data. Okay, and it turns out that we also have such mechanism in relational databases. For example, in Postgres, this is called channels. Okay, a channel is like a queue. It will have some producers and some consumers on the other end of the channel. Okay, so we will use channels here. This will be the second ingredient here. Okay, so now we have 2 ingredients. If some row is inserted into the table, a trigger will be awakened. A trigger will call some function, and that function will push the data onto the channel, like without necessarily caring who will receive the data. Okay, so we have 2 out of 3 ingredients, and now we would like to consume the data from the channel. But how can we consume the data from the channel, from the PostgreSQL channel in the JVM application? And one of the options is to use skunk library. Okay, so skunk library is still work in progress. Okay, so you should be careful with skunk at the moment, at least. But skunk already provides a way to communicate with PostgreSQL channels. Okay, what do we need here? Okay, so first of all, we need to create a session. A session is like a handle to the database. As soon as we have a session, we are telling that we are interested in communication with channel called offers. Okay, then we are saying that, okay, we would like to listen to that channel. Okay, at this point, skunk returns us a stream of notification of string. Okay, it's a stream from FS2 library, which is basically like a stream of notifications coming from the database. Okay, and since in my applications I'm very often using Monix library, I'm also showing you how can you go from FS2 stream to Monix observable, and this is possible thanks to Reactive Streams protocol. Okay, which is like a bridge between many different implementations of stream processing libraries. At the end, after all those operations, the resulting data structure is observable of notification of string, which is a possibly infinite stream of data coming from the database, of data being pushed in the direction of the application by the database. Okay, a thing that is worth mentioning here is that if there's no data in the queue, we will not be blocking any JVM thread. The whole process of waiting for the data in the channel will be performed in an asynchronous and non-blocking manner. So as you can see in this example, relational databases don't have to stop us from going fully reactive, fully non-blocking in our applications. It's possible. It's possible in such use cases as well. Okay, and as I said, there are also some attempts to provide a generic solution to non-blocking communication with relational databases. The first attempt to solve that problem was called ADBA. I've used the word was because it's not developed anymore. It was an initiative by Oracle, which was supposed to be like the extension to JDBC that will provide some asynchronous capabilities to JDBC. The API was supposed to be organized around Java's completable future, and it wasn't supposed to support like streaming, back pressure, and all of that. Okay. Last year, however, Oracle decided that they will no longer be developing the solution. Instead, they will wait until Project Loom is released. And the reason is that if Project Loom, or when Project Loom is released, all the existing JDBC calls will basically be non-blocking for free, okay, like out of the box, because a blocking JDBC call running on top of a virtual thread from the Project Loom will not block the underlying thread, the underlying JVM thread. Okay, so this will be like this will be the solution which is available out of the box, mainly for free. The second approach, the second solution was an initiative, or is an initiative by Pivotal, which is the company behind Spring. And the API of the solution is organized around Project Reactor. So the API will have like mono and flux in the returned data types. Project Reactor on its own is compliant with Reactive Streams protocol, so it will be very easy in our Scala applications to go from Project Reactor to FS2 stream, Monix observable, ECA stream, and all of that. Okay, and the first release of R2DBC was presented in November of last year, and I will show you two examples of using R2DBC. The first one is like an implicit approach, and it's very Java-ish. That's why I've also used Java here. Here in such solution, we are expressing our query inside an annotation, which is not so popular approach in the Scala ecosystem. And as you can see, the return data type is flux of offer, which is basically a stream of offers coming from the database. Okay. And the second type of usage that we can have with R2DBC is like an explicit handle to the database, where you can explicitly call a query from inside your code. And as I said, you can very easily, thanks to Reactive Streams protocol, go from like Project Reactor's flux to Monix observable FS2 stream and all of that. You can basically hide from the rest of your application the fact that you are using R2DBC in the first place, or that you are using Project Reactor in the first place. This might be an implementation detail that doesn't leak into any other part of your application. Of course, there are two drawbacks of that. The first one is that you will have Project Reactor on the class path. And the second problem is that you will have, unfortunately, many Spring dependencies of the class path but it is possible to use R2DBC from Scala in a way that doesn't affect like the rest of the application. Okay, and I think that we should have a break now because there are 40 minutes after the presentation started. So enjoy your break and we will see in 20 minutes.